Hello, I'm David from ncd-group. Today, we're going to look at how the fourth tab of our simulator works, the Gravity Assist and Orbital Transfer Planner tab. Before anything else, and to give some context, we recommend downloading the attached PDF documentation, a 16-page document that explains everything from the basic concepts of Gravity Assist and the formulas used, to specific examples like the New Horizons mission and the famous Grand Tour of the Voyager 1 and 2 probes in the late 1970s. The manual also includes a comparison between the data generated by the simulator and the real data provided by NASA over the years. Lastly, it gives a detailed explanation of how the software works internally through the mathematical apparatus used, and how our orbital engine calculates things like launch windows available near your chosen launch date, arrival dates to the flyby targets, and the incoming and outgoing velocities at each point. Once we're ready to test the orbit simulator, the first thing we need to do is choose a flyby target and a final destination, or two flybys and a final destination. Let's start with the long route. In this example, we'll choose a second flyby. We'll leave Mars as the first flyby, Jupiter as the second, and the destination will be Saturn. The departure point in the simulator is always Earth. Next, we select the launch or departure date for our probe and set the playback speed of the animation. At speed x1, 1 second of simulation equals 15 Earth days. If we multiply the speed by 10, then 1 second will equal 150 Earth days. Then, we choose the launch velocity. The selectable velocity ranges between 0.9 and 1.1 times the solar escape velocity from Earth, that is, between 39 km per second and 46 km per second from a heliocentric frame of reference. It's recommended not to change the deflection angles, delta 1 and delta 2, in the upper left part of the menu. The simulator is capable of calculating the optimal value to reach the target. All of this is thoroughly detailed in the attached documentation. Now, we click the Simulate button. In this example, the heliocentric launch velocity is 40 km per second, so this is a Hohmann transfer or elliptical transfer orbit. The first thing the software calculates is the earliest available launch window for a possible alignment or encounter, and the arrival date to the first flyby, Mars in this case. In the bottom left corner, we get a graph showing the drop in both the solar escape velocity and the spacecraft's velocity, according to mechanical energy conservation principles. When we arrive at the first flyby, Mars, the expected happens. The simulator tells us that we must undergo a deflection of a certain amount to reach the next object, Jupiter, in this case given the positions of Mars and Jupiter. The deflection is -139 degrees relative to the radius vector connecting the Sun and Mars. This deflection will affect, as seen in the formulas, the spacecraft's change in velocity and the minimum approach distance needed at flyby 1. Now that we've entered the recommended angle suggested by the simulation engine into the spinner labeled delta 1, we click Simulate again. Now the correct deflection occurs, allowing us to continue the trajectory to the next target, as shown in the animation. At the bottom of the screen, there are two buttons, Stop and Run, which allow us to pause the simulation at any time for data analysis. We can see how the spacecraft's speed increases after the gravity assist. The orbit is now no longer elliptical, but hyperbolic, as shown. The journey continues to the next flyby, Jupiter. Now we can see that the simulator provides us with more data, including a new velocity profile for the spacecraft. This is because the simulator internally iterates step by step to determine the real-time positions of the objects, in order to find valid launch windows and target alignments. Finally, upon reaching flyby 2, it again recommends a delta 2 value needed to reach the final destination. We follow the recommendation, input the value, and the simulator recalculates everything: departure dates from flybys 1 and 2, arrival date to the final target, approach velocities at each flyby, minimum distances at those deflection angles, and the final arrival date and speed at the destination. In the final part of the video, we show an example using just one flyby and one final destination, in this case, Mars and Saturn. The positions of the planets over time are made possible thanks to NASA's New Horizons program. Thank you for your attention, and happy space exploration.
If you like our content,